So welcome to the pre-recording of lecture 9 of MCS 260, running in the 8-week summer session. So this 8-week summer course has sessions of 2 lectures as I organized them. So this is our 5th session at the end of the 2nd week. So there are 3 parts in this lecture. I want to explain why the binary number system is so prominent, and actually we will give a definition of a computer as a synchronous binary digital system. So that's the first part, mainly slide presentation. In the second part, I will first also introduce with the slides the intrinsic operations. Intrinsic means part of the standard library. Operations on strings, operations on lists, and as an application, I will show how to make a dictionary of the characters in a string, a frequency table. So a frequency table by means of a dictionary. So this is a programming course as well. So in the intrinsic operations, I will illustrate them with a Jupyter notebook. So in a way, we are then using Python to compute a frequency table. In the second part, we will also compute something, but what we will compute will actually be a string. If you write out a check, or even if you are going to a bank to make a withdrawal, often the teller will make you write out the number in words to kind of avoid any ambiguity that may occur by a sloppy writing of a number. So we will see a program that will print out numbers in words. So transforming information is something that is a central task in computer science. All right, what is a computer now again? Well, here is the definition. The definition is important in the sense that it not so much literally important, but if you can memorize the sentence, similar to what is an algorithm. So computer is synchronous, so there is synchronicity, so there is a system clock that is actually going to determine the order of things. Also, the speed of the clock is an important characteristic. It is binary and digital. While our models of the world are often continuous, the computers that we are using are digital. So all the information is discrete, and everything that we manipulate is actually a sequence of zeros and ones. So this is where the binary comes in, and where the bit is a contraction of binary digits. How come? Transistors are used to build computers. So they are the electronic circuits. And because of that, and in the next lecture, I will say how the data is actually stored by latches and how things can be latched, but let's not run ahead. Let's talk a little bit about transistors now. So a transistor is an electronic circuit. It can be used to represent a bit. So there are 2 states depending on whether the switch is open or not. So high voltage when the switch is open, low voltage when the switch is closed. So there are 3 parts. So these are oversimplifications. So in the diagram you see the B for the base. This is where the input is. There is the collector that will give the output. And the output can either go to the directly from the base, from the input to the output if the switch is open. Otherwise, it is emitted to the ground. So that third component of the transistor. Okay, there is a direct correspondence between the elementary logic operators, the ones that we considered in the previous lecture, in the previous session, the not, the and the or, and the electronic circuits. So the electrical engineers use these symbols. So we've seen flowcharts that are pictures of algorithms. There are also pictures of what a transistor is doing. So we have the elementary circuits, and actually, as we will see, the elementary circuits, there are actually the not and the not or gates. So there is this empty circle in the not operator. So we have the and the or symbols. So you can see the not is a unary operator, only one input, and an or are binary operators, take two inputs, have two operands. Okay, so when you can build the not and the not or, then immediately by adding a not to it, then you have already um, the and the or operation. So in some sense important, the and the or are actually not the primitives of the transistors. So to make an and or gate, you actually need multiple transistors. Here is a not gate, so it's kind of a little bit strange that we start with the not. We are starting kind of negative, but it's easiest to explain. So not gate switches a 1 to a 0 and a 0 to a 1. So there is the input voltage at the base and the output voltage at the collector. When the switch is open, then actually the low voltage becomes at the output we have actually the V infinity there, which is a huge voltage moderated by a resistor. So when the switch is open, then actually we have that the output is the V infinity. If the switch is closed, then actually if you have a high voltage, then that high voltage will actually still, with a closed switch with the resistor at all, the output voltage will be low. So this is not my strongest suit here, the transistor explanation, but I hope that you kind of get the picture. You can put transistors in series or in parallel. So if you put them in series, we have then a not and gate. So there is again the switch there. Whether the switch is open or closed, the output voltages will correspond to the not and gates. So I will not go in great detail through what is actually happening. So it's mainly important that the not and gate is a basic operation that needs two transistors that are aligned in series. The NOR gate is by putting transistors in parallel. And perhaps I should have indicated this earlier. If you have a transistor, there are two different modes how to combine them in parallel or in series, which explains the also binary nature in the operations, either an AND or an OR, a not AND, essentially when you are in series, not or when you are in parallel. So we have the input voltages, and then it depends on what the switch is, whether the output voltage will be corresponding to the low. So here, when the closed switch, remember that the OR is only true when, sorry, is only false when both operands are false. And this is also, here we have the not OR gate that is represented. So okay, transistors. Now the second part of the lecture. Um, Intrinsic operations. So Python comes with batteries included. Data structures are often determining the kind of programs that we write. So programs are algorithms and data structures. In this third part of this lecture, I will illustrate how dictionaries and conditional statements are joined together. I indicated earlier on that dictionaries are the counterpart data structures to conditional statements. But in order to have something that works, anything that works is typically a combination of many good ideas. Here is the introduction to the intrinsic operations. So we've seen earlier that the split and the counterpart, so the opposite, the join, not the counterpart, so the split and the join are very good to know if you want to do format conversions on strings. Um, Strings are very basic data types. Actually, Python views them as um, elementary data types because they are so fundamental in many operations. Um, Despite that, we can also view them as sequences of characters. The intrinsic operations. So we talk here about operations. Python is object oriented, and there are methods and there are functions. So operations refer both to the functions that we have, so the ID and the type. So everything has a type. Every variable, every object not only has its value, but also the information about the type of operations that you can do on a variable. Uh, Type returns gives you the logical representation. Idea gives you the identification of the variable, and this can be used to go to the physical location, the address of the variable, where the data is stored. So this dual vision idea of X is something that we actually are not really going to use that much because of the garbage collection. We don't really need to know the actual location of where things are in memory. Although if you would be doing interface coding, this would be extremely useful to know. But the type is very important. In interactive computations, we can actually check on the type of something. So I mentioned that strings are very useful data types. So they come with a very extensive list of operations, and even I have to look it up. So if you, in an interactive session, you can type in dir to see the list of all the operations that are provided on strings. You can do help and then str, so str is the name of the type, and then split to know more about a particular operation. You can always Google it or ask ChatGPT, fine, but it will not beat the online help that you have with the system. So know that these operations are available to you. All right, so I will introduce now the third part. Um, Here is the application. So suppose that you want to write a paper check, if you're still doing this, or you want to write a natural number into words. So 125 is actually spelled out in detail as 125. So this is the example. What is the program specification, the input-output statement? It will be a natural number, so no negatives. And also we don't go above 1000. It would be an exercise to work with many larger numbers. Could be useful if you have an application also that wants you to spell out, to read aloud a number. So the output is thus a string. So we go from a number to a string, although the number when it's typed in, 1 to 5, is also a sequence of characters. What's the idea? So with the slides, there are the slides, there are the Jupyter notebooks, and then there are the Python scripts. As a programmer, we actually want to go to Python scripts. With the slides, I want to illustrate the ideas that are leading to the Python scripts. So at first, it seems like a daunting task, but think about all the special cases. The numbers in English, so actually the first, uh, so what is actually missing from this 18 seems to be missing. I don't know if that is a spelling, if that is an oversight, or I will check the code. It just dawns to me. But if you think about the numerals going from 0 to 10, that actually can be solved by a dictionary entirely. So it could be possible, and then if you actually really don't want to use conditional statements and we go to 1000, so you could be very fastidious and define a dictionary with 1001 keys, but that's not very nice and actually quite error prone. So you see, even here on this slide I omitted the 18. But the point being is that in English it is kind of irregular up to 20. So the first 21 cases, you have to uh, define them by a dictionary lookup. But then 37, 35, 33, these are all very irregularities. So the numbers in between the multiples of 10, they can be handled by an algorithm. So, and that requires much less code to define rather than a static data structure. So in a way, this application is important to decide when do you use a dictionary and when do you use conditional statements. So here is then the case analysis. So in the last lecture, we had the if-else test. So we have the trivial case. In case our number is n equals 0, we have 0. Then we have the large numbers. We do then division and remainder. So I'm getting the large numbers first because you first want to check actually when a number is larger than 100 or not. If it is larger than 100, you capture the leading digit. So we don't go above 1000. So any of the, and that's why also 0 is actually important. You don't want to write 0, 100. So you write 100, 200, 300, etc. And then you deal with the remainder. The fact that the remainder is case number 3, and it might have been more logical to uh, have swap the second and the third case. But the third case is also a case you have to continue with for numbers larger than 100. So the case for numbers less than 100 is similar to the remainder of large numbers, larger than 100, and the special cases. So you will do a remainder computation for any number that is larger than 20, strictly larger, and but otherwise you will do the dictionary lookup. Okay, so here is then the flowchart. Um, It looks complicated, but it is complete. And in some sense, it's rather dense because the slide didn't really allow for bigger room, but it's still something that fits on a slide. And if you have a larger sheet of paper, you can see the structure. So, I mean, so if a larger sheet of paper, it might be a good exercise to actually think about the logic based on the case analysis. So when you draw a flowchart, so I did it here in the LaTeX, but you can also actually do it with the diagram. What you actually do are first write out are the diamonds, are the tests. So we test on whether a number is 0, then we have just a special case. Also, if you write your program, that's actually, you write it in bits and pieces. So the case equals 0 is something that is the base case, the ultimate base case, the trivial case. Then we have the other two tests. If the number is larger than 100, you can have 300. So there you have the test on 0 again. But now actually, if you have 300, you don't write 300 and 0, you just write 300. So if the remainder, so we replace the number by its remainder. If that remainder is 0, then actually we stop. So we write 300 as 300. So you see already from these first two tests, we can already handle 0, the trivial case, and all the numbers that are multiples of 100. So the number that you write before 100 is a dictionary lookup. All right, then comes the remainder computation. Again, if the number is 20 or less, you have the special case. So 318, you write as 318. So the pseudocode is still pseudocode. The and is here omitted. So you will write 318 if you literally follow this flowchart. Then we compute the remainder, so just in case, we compute so if we have to compute, so if we have 33, we have to write 30 and 30 and 3. So these are now the two cases. So the n is the number that remains after division by 100. So we write either the entire number, or then we write, so if the remainder is 0, then we can just write, it's just a lookup. So if the number is divisible by 10, the remainder by 10 will be 0, then we can write 30, 40, 50. Otherwise, we have to subtract the remainder. So 33, we have to subtract 3, the remainder, after division by 10. We have to subtract this. And we have to write this down. So the flow chart allows us to check that we have covered all the cases. So in some sense, you can do completely without the flow chart, but the flow chart will be extremely useful if you are frustrated by all the syntax errors in your program. The flow chart is extremely good to check all cases. We will see loops later. The real check is essentially building a loop. So here you can still be very exhaustive and list all the numbers between 0 and 1000, um, ending by 999. Here you can spot check things, so take special cases uh, to make sure that you cover all the cases. Okay, I will show the solution to this, but after the Jupyter notebook on the intrinsic operations. All right, the purpose of the lectures is that you get access to, that you understand how to do the exercises. Um, the first exercise is if you're more hardware oriented. So we have the not or gate, the transistors that you need there. So you have two transistors in parallel, but then you still need a not. Describe all the transistors here. Constructing truth tables, which is essentially an exercise that comes from the previous lecture. Um, you can also look at these logical expression and describe all the NOT gates, all the logic gates that are realizing the expressions. So truth tables are still very important to check if you see the AND, the OR, and the NOT, but actually from an electronic circuit perspective, you would like to rewrite this by not AND and not OR gates. So in a way, if you are thinking in terms of transistors, you may want to first prepare your rewriting of the logical expressions in the not AND and the not OR gates. So these first three exercises are for the first part of this lecture. We introduced little games last time. Uh, there is a number guessing game, so you can um, generate a random number and then prompt the user for a guess. By printing feedback, you can be very terse to the user and just say true or false if it's right or wrong. But you can also say the number is too low or is too large. And this allows for the user to apply a binary search. So that's a good exercise also to have an if-else test here. We introduced DBM. You can store that dictionary on file rather than storing it in the program. Um, most programs actually consists of many pieces, and you could eventually, and we may be doing this in a later stage in this course, you could actually build a layer on top of the numerals. So you could build what we will call an interface class on top of the data structures. All right, let's go into the intrinsic operations now. So I have prepared a Jupyter notebook rather than me giving a hands-on demonstration. Um, so if we prompt for a number, we and we want to compute with this. So the number actually first comes to us, the programmer, as a string. So the result of input is a string, and then we have to cast it into an integer. Now, if the user makes a typing mistake, types a character or hits enter too early, then actually you may have wrong input. So you can actually check whether the input is actually a valid number. So this is the test is alpha. So if the number is alphabetic, so also if you ask for a name, a valid name without any digits in it, then the is alpha will return true. In the case of saying an integer here, if the number consists of digits only, then you will have true. We will introduce loops, so you can use these operations to ask the user to retry rather than to abort the program. We can check whether a string is alphanumeric, so whether it doesn't contain any special characters such as a comma or a dot. So alphanumeric is whether there are either numbers that are letters, that there are strings where there are consists of letters or digits. So here you see a test for which the is alpha fails. Okay, this might get a little bit boring, and you can see with the dir how much is actually available. There are the double underscore, so you can see there is the add operation. So this is the plus. The plus on strings concatenates. And you could also actually write, instead of the plus, you can actually write underscore underscore add underscore underscore and do that. You can also multiply strings. So that means that you do many repetitions. There are other operations. So here you see the indexing, the counting, the join is in there, the is upper and the is lower. So just do dir to see if an operation is supported. So you can say start with, you can split on the lines, you can split. So some Python is case sensitive, but some words, if they are lower or uppercase, they actually mean the same words. So if you prompt for a name and you want to save the name, check whether the name is in there, you may want to canonicalize or normalize the string, either convert everything to lower or convert everything to upper space. Slicing, so in some sense this indicates that strings are actually not really elementary types like numbers, but just as numbers can consist of many digits, string consists of many characters. So you can, with slicing, you can select a character or select an entire piece, like everything other than the first character, convert the first character to uppercase, and then concatenate the two strings again. So seeing a character just as a string is very convenient when it comes to the operations. We can check whether a letter belongs to a string, and here hello has two L's. At position 2, so we start counting at position 0. At position 2 we find the first L. There are two L's, so we can count them. So we will go back to frequency tables as an application. So this may rather seem boring, but still it's often important. So these are also important programming exercises. If you are unaware of these string operations, you can actually implement them with for loops, with selecting characters, and also by testing, by conditional expressions. And you can check your result. So counting the number of characters, that is a non-trivial operation if you don't have that count there as a programmer. But as a Python programmer, it's actually much more convenient and you will be so much more productive if you know these intrinsic operations. Split and join, if you want to do format conversions with dates, with times, then this is very important. If you have a timestamp, the current time as we've seen before, and you want to extract from that the hour at which the timestamp was created, you can do this with a split, which returns you a list. You can select from that list. Or here, sorting is extremely important. I mentioned binary search with the secret finding. If the data is sorted, then the search goes so much more efficient. The in operation will actually not assume this. So, or finding the index something, this will be sequential. Um, Sort is an operation, but it counts as a method. So we distinguish operations between functions that do not change, like for example the minimum and the maximum element, here with the alphabetical order. So min and max are operations that are functions. The sort is a method, so it has the ability to change the list, the argument. Reverse is something that is also being used. Okay, strings, lists, tuples, and dictionaries. So let's use them all at once and build a frequency table of characters in a sequence. So we do have a string, and know that a dictionary what is a dictionary? It is a set of tuples, and every tuple consists of a key and a value. In our frequency table, the keys will be the characters that are in the string, and the values will be the count. And um, essentially, it's one statement to make the data for the frequency table. So we have the list of tuples. For every character in the string, we count how many times the character occurs in the string. And that gives you a list of tuples. So we've seen last time how you can make dictionaries and how you can select from a dictionary the list of keys and the list of values, and then you can zip these two lists into a list of tuples. Here we have automatically a list, and we can actually split that, but the problem is the duplicates, the duplicate elements that we have in there. Well, we can fix this with a dictionary automatically. So if you convert to a dictionary, and again, if you don't know about the dictionary, this is a non-trivial programming exercise. So the reason why this is so useful to know is that here with essentially two lines, so the line 32, so the line 32 makes the data, the list of the tuples, and then the line 34 applies the constructor. So in the object-oriented language, it is a constructor, but you can also see this as a type conversion. The type, the list of tuples, is converted into a dictionary. Dictionaries that are viewed as sets. So a set essentially doesn't contain any duplicate. If you now want to know which letters are the most frequently occurring, well, you ask for the values and you also ask for the keys. And then you select the minimum and the maximum. And with that minimum and maximum, you go back to the keys. Here it is we didn't have too many characters in there, so you can eyeball it. But you can also sort your values by converting back into lists of values, and then you sort them. You can also sort, and the sort method is actually something that can apply to tuples as well. We will get back to that, or if you are curious, you can look it up. Look at the documentation for sort. You can, for example, you can sort tuples first on their first element alphabetically, and then you can sort on the second element, their value, or you can do it in the other way around. So you can revert. Perhaps I should not talk too much about this because we have already covered this. And I should spend time now for the third part, which is the application of writing the numbers. So let me go back to the slides. So here you see the flow chart, the ID for the algorithm, the dictionary, and the program specification. So let's look into actual Python code to solve this problem. So here is the complete exercise, and now I see that there was not a bug in the program. I probably mistyped it, or I did some formatting and the 18 disappeared. But here you see that the 18 is part of my dictionary. That's a relief. Um, So every program I start with a comment. So what does the program call? What is the program called? And a documentation string. So what this program does, you could also formally write the input output. So the user is prompted for a natural number that is converted into uh, integer. So the string data becomes an integer. Um, I'm building up the outcome. So at the very end, the output at line 34 here, the outcome will be printed. So when you develop this program interactively, please run it already. So as soon as you have prompted, and especially here with this dictionary, if you make type errors, if you forget something, um, I mean, if you are making modifications of this, you would do the copy and the paste. But if you are typing this up, please test this frequently and often. With the Jupyter Notebook is extremely useful for this. So you can type this into a code cell, like I did with the mileage table in the previous session. Type this into a code cell and then query it. So running it through a code cell is a way to effectively pre-parse this. All right, remember the flow chart. The base case, the very trivial case, which you should not forget, is the zero case. So if the number is zero, then you will add zero to this plus equals. Here it is a very abbreviated way of writing that I'm assigning to outcome the concatenation of outcome and the result of the dictionary lookup. Which means that I'm starting with the string that has already a space there. So 0 is 0. So that is the first case. Again, if we are running this, please test this. I'm not running things here because I do not want to run over time. Python. In going from Python 2 to Python 3, the integer division returned a floating point. approximation. So when I went from Python 2 to Python 3, I had to fix the output and the input and the output. So, but also I had to change the integer division. The fact that input and output became functions, that's okay. But the fact that the integer division changed is kind of cumbersome. So if you want that, if you divide 315 by 300, you want to see 3 with the integer division in this application. You don't want to see 3.15 because that would lead to a key error in the dictionary lookup. Okay, if the number is larger than 100, the outcome will be the lookup of the quotient, so 315, we will look up 3, and then we will add, separated by a space, we will add the space to it, we will add to it 100. So we will look up the word 100. In some sense, it's a little bit pedantic. You could have said that you may as well just write the string entirely 100 to this, but it's more in line with the dictionary lookup. Then you compute the remainder. So notice this is one if statement. So there is a condition that comes after the else. So you could also have, I could also have written else if, that would have been longer. But the else if we have with multiple cases. So here we have the else if there is an else with a condition. So if the number is larger than 100, we have to write 300 and compute the remainder. So the number here is assigned, the input number is overwritten by the remainder. We have to write and if the remainder is different from 0. You see, if the remainder is 0, then the other if will not be executed. Notice that the number of spaces in front of every statement matter a lot. So we will execute that if no matter what. So you could think that, so remember the cases. So trivial case 1, case 2, it actually also runs over case 3. So case 3 and case 2 share code. Again, we will see functions. There might be a neater way to have the logic better. But then also we have duplication of code. We would need to repeat if we say we treat the middle case, the third case, the numbers between 0 and 100, 0 not included, 100 not included, if we treat this as the second case. And in the development of the program, that might be perfectly excellent practice. You first deal with the cases that are the special cases, the numbers 0 to 20. That's actually defining the dictionary. And then you deal with all the numbers that are kind of in between. And then you deal with the numbers larger than 100. And you observe that in dealing with the special case, you actually do have the remainder case that is separate. So this is an application, and there have been several iterations that were needed to get to this final result. That's some remark that I want to leave you with in the last minute. So I'm presenting you with a complete program, but there have been many iterations to get it to this final result. I should end by actually running this. So I actually had an alpha test. I reworked this in the right. I may post this, but this is the alpha test to check whether a number is really consisting of digits or not. All right, writing of the numbers. So 318 is spelled out as 318. Another way to work with this program is to write many print statements. So you can trace the execution of the program, trace the logic by writing print statements. So in which case you are here. Okay, I'm running over time. I hope that was not too overwhelming, but Python offers a lot of tools to write interesting programs with a very limited amount of source code.